All right, welcome back. We're going to do two important trig limits today. All right, so let's start with this guy. This is something that we'll need to know soon, what the limit of sine theta over theta was. Okay. We actually had investigated this numerically and had convinced ourselves the answer is probably 1. Now with the squeeze theorem we can check that this is indeed correct. So recall that we had this geometric result. The cosine of theta is less than or equal to sine theta over theta, less than or equal to 1. And so you can see we're going to squeeze the middle guy because we know what's going on with the two endpoints. Also, the limit as theta goes to 0 of the cosine of theta is 1, and that's because cosine is continuous. You can just plug in theta equals to 0, cosine of 0 is 1. And of course, the limit as theta goes to 0 of 1 is 1 because it's a constant. It's not even changing. It just stays at 1 forever. So, by the squeeze theorem, we get this, that the limit as theta goes to 0 of sine theta all over theta is 1. So this will be an important identity that we'll use later on. All right, we need a version of this for the cosine as well. That one actually has to do with this. The limit as theta goes to 0, 1 minus cosine theta all over theta. We need to calculate this limit as well. And this one involves a trick. And the trick is just this. We can multiply the top and the bottom by 1 plus cosine. Since that's the same as multiplying by 1, it doesn't change anything. But what this does do is changes the top to 1 minus cosine squared of theta. And that's really why we did this. Because we have this trig identity. Remember, cosine squared theta plus sine squared theta is 1. Right? And that just says that these are the coordinates for the unit circle. So anyway, that top is really a sine theta. Sine theta squared. And I know how to handle sine over theta, so let me put those together. Okay. Here I'm using the limit of a product as the product of the limits. Guess that should have been sine theta. Anyway, we just calculated that this first one was 1. Now the second one, actually we can calculate because when you plug in, first of all, the top and the bottom are continuous, and the denominator, the bottom, when I plug in 0, it just turns into a 2, so it's not 0. So it's continuous. I can just plug in theta equals to 0 everywhere. So I get 0 over 1 plus cosine of 0, which is 1. So I get 1 times 0 over 2. It's 1 times 0. That's 0. And so this gives us our second important trig identity that we'll need later. The limit as theta goes to 0 of 1 minus cosine theta over theta is 0. All right, we'll need that one later. All right, so now we're just going to do some applications of this that come up sometimes. Here's, or more precisely, examples. So let's look at this one. The limit as x goes to 0 of the sine of 4x all over x. Now remember, I know that sine x over x will converge to 1 as x is going to 0. That's not the problem we have. So this result isn't helping me yet, okay, because it's a different result. And the trick is to make a change of variables so that this 4x, becomes as if it were just an x. So let's let theta be 4x Another way to write that is it's saying x is theta over 4. Okay, same thing. So then this limit will also notice that, of course, saying that x goes to 0 is the same as saying theta goes to 0 because they're just multiples of 4. So if x is going to 0, then theta is going to 0 because it's 4x. And similarly, if theta is going to 0, x is going to 0. So they both are going together to 0. So saying the limit as x goes to 0 is the same as saying the limit as theta goes to 0. But now let me change everything into thetas. So this will be sine of theta because the 4x was theta. But the x turns into a theta over 4. Okay? All right. So this is the limit as theta goes to 0. The 1/4 in the denominator just is a 4. This is good news. Remember, constants, the 4, pulls outside the limit. And we just have this, the limit of sine theta over theta. And that's exactly the thing we figured out up here. All right? So that thing really is 1. Okay? So what we showed was that the limit as x went to 0 of sine of 4x all over x was actually 4. It's actually pretty easy to do this replacing 4 with like a k to see that the limit as x goes to 0 of the sine of kx all over x is k. All right, that's it. Ciao.